forget about this. I'll just let it flow in the internet. That's great. Yeah, so okay, that started. Sorry guys, like the first minutes are a bit of like organizational. I saw that it's great that you know how to interact on Zoom. Feel free to add questions or comments or talk to me through the chat log or just speak over me. It's totally fine. Let's be informal. Oh wait, sorry, I had. Oh no, I hear myself under. Okay, sorry, I had to close Zoom. Otherwise, I could. That's why I stopped. I was like, who's talking to me? Myself. Okay, fine. So, your reactions. I have some poll questions for you as well, and like let's try to interact as much as possible. I'll start sharing my screen so that we can see what's going on here. I mute everyone at the moment just to be sure that I'm not hearing. Here we go. Excellent. So I've shared with you this folder related to the workshop. We'll meet 5 times, and we have organized for you guys short exercises to build skills in robotic fabrication. And while I'm going through some of these things, where's the control bar here? I would like to send you a poll so that I have a sense of your current level of expertise. Respond to that, let me know. We have a daily schedule, and I'll go through a couple of things and also a short introductory lecture. So this is an introductory course to robotic fabrication. This is run remotely, but we have the support of the Fab Lab, of the B Lab at Lawrence Tech College of Architecture and Design in Detroit area, Southfield in Michigan. So it's kind of like we're getting connected to get some stuff done this week. And hopefully this workshop will help you guys build some good content, good images for your portfolios. I'll start from the daily schedule. I had that open already. Okay, I'll go through this real quick. So again, my name is Sara Clederin. Nice to meet you all. I'm from Italy. I'm currently teaching both in Italy and in the US remotely. I'm in Ferrara, which is in the northern east of Italy, near Bologna, and my education is from the University of Ferrara, where I've also obtained a PhD in robotic construction. I had the pleasure during the PhD to spend some time in Detroit. We'll talk about that. There's a great culture of manufacturing in Detroit. It's a great place to be, like to understand these things, to understand the fourth industrial revolution and the consequences in design. And thanks to my in Detroit, I spent some time at LTU to use the tools because my university in Italy is very theory-based. So I did some application there, and I met some amazing people that are helping us through this workshop. So I see that Misery Jeff maybe will join us later. Jeff is the beloved expert at Lawrence Tech. We have here Emily, who I listed as a TA. Do you want to introduce yourself, Emily? She's gonna help us.
Sure, I can. Yeah, I'm Emily. I'm going to be a third-year architecture student at LTU, and I was able to take Sarah's prototyping and fabrication class this past spring, and I really loved it. So now she gave me the opportunity to help you guys out learning about the robot and stuff, and I jumped on it because I wanted to learn more about the robot and to help you guys out with the same thing. So I'm happy to be here.
That's awesome. Thank you so much. And Emily did great in the rubber fabrication class, so she's added value to this. Thanks a lot, and she will be the connection between us and the Build Lab in the implementation of your files that you will produce in these days. I'm seeing meanwhile some responses. That's great. You've never programmed a robot, never ever used Kuka PRC. Oh, that's great. That's great. So there's room for improvement this week. There's one parametric design wizard. I'm looking forward to seeing your what you'll be able to produce. Unless that was Emily. Did you respond that, Emily, that you are a parametric design wizard in the survey? No, that wasn't you. Great. But that's exciting. So another thing, did you guys install Kuka PRC? Okay, no issues. Okay. In case, let me know. We'll solve everything. There's no problem. Okay, some reactions, thumbs up. Okay, awesome. So what are we gonna do? We have 5 assignments, 5 short assignments. We'll spend some time during the live sessions working, but also I'm giving you a bit of homework, but it's stuff that is totally manageable, it's fairly simple, and these exercises will lead to sort of a final proposal that sort of we would like to guide you, build robo skills, programming skills, and then have the possibility to think about the robotic process to build, let's say, an architectural, technological unit, an architectural component, and imagine how to produce that component, imagine it applied at a larger scale. I'll support these things through images in a second, but just to tell you, we are here today. I'm showing you some software demos. I'm sharing some like introductory information about like the meaning of robotic fabrication, and then at the end of the day, I would like you to submit one image, basically one of our images or drawings of the robot. Like I call it digital twin, is a digital representation of the robot because it's good that you learn how to do that. So it's like in terms of like showing and representing and communicating the process that you have in mind, just learn how to represent the robot in the digital space. I'll go through these other things day by day, each day. And yes, and the goal will be at the end to be able for you guys to speculate on a robotic process applied in architecture, and we will discuss at the end. So sort of like what I have in mind, and you can see that through the organization of the folders, is that, well, that doesn't count because there's no submission of the running grasshopper files, but we would like you to submit your files running grasshopper, and then there's a template. It's very simple in which you drop your material, and every day we will discuss a little bit the results. So it's the same applies to the final submission. So we'll go through the slides, drop your images there, and possibly also the files, especially those that we will process in the Build Lab. You can find, there's also, if that helps, we have here a spreadsheet with a bit of like, like the titles of the sessions. I've set, just for consistency, the deadlines in terms of 3 p.m. in Eastern time, sorry, Detroit time, 9 p.m. European time, 3 a.m. China. I don't think that at this point there's anyone from China, but like this means basically before next day or like early in the morning or before the next session. It's just for the consistency in terms of like the span of the time zones, the amount of hours. And you will produce a couple of things, and we will document those things for you, and you can use them. We'll deal just with rubber programming first. We'll produce some robo-like painting, and Emily will guide us through the workflow to realize these kind of images. Hopefully you learn as much as possible, but like we won't deal with materiality right away because it's difficult, because you guys need to understand certain things first. But then we would like you to produce something, a form, hot wire cutting process, and then those are things that you can just exhibit. Not like in physical terms, but at least as documentation. And of course, let me know if you have questions, drop comments in the chat log, let me know. What do you want me to do, Emily? That's enough? Did I cover enough? Should I go through the lecture? Yes, you agree? Okay, fine. Okay, so let's go here. And let's start from, no, that's not the lecture that I wanted. I need to just to see what the following slides are. Here we go. Okay, full screen. Yeah. So I introduced a bit these things. That's the context. We were contacted by the DigitalFUTURES community, in this big event with the aim of share knowledge as much as possible throughout the world. And we are testing also opportunities to teach digital fabrication, robotic fabrication online, and we are trying like step by step to improve the process, so that it's a challenge, but because the materiality is sort of like missed, but at the same time it's important, and it's great to share anyway these kind of processes. So, well, this is the workshop, and just to give you the context, you will work with this guy. It's the LTU's robot. He's a guy. His name is Bianco, which means white in Italian for obvious reasons. And we'll talk more about the fact that in the Detroit area, robots have a second life in school. This robot comes from the automotive industry. It's a second-hand robot that was used in academia and was used in higher education. And that's the way we started. That's actually the first course that we taught at Florence Tech. That was myself with Carl Damman, that hopefully Isadine at LTU will give a lecture this week. And these are some outcomes from like a robotic fabrication class that we framed within the fourth industrial revolution, and we framed in a way that to us allowed us to talk about the notion of the master builder, meaning the architect, the designer, who's able to understand production, who's able to understand materiality, who's able to understand downstream processes, like from design to construction. We've been through the the daily schedule. And as I mentioned, you will produce two things. And that's, we can try to do more. I don't think it's possible knowing the workflow, but like you, at the moment, we have a crew of like 12 people, and it's fairly simple, the fact that we'll be able, like in one day, to process 12 scripts or even more if other folks are joining soon. And so you will produce one light bright exercise, a robo light painting, and one hot wire cutting exercise. This is one the form typology that we explored earlier in the course, in the class. But you can think of even like different ideas, different forms, curvy, linear forms. There's room for exploration, and I will explain more about this in the future. But let's start thinking about a final assignment. So I'll get you through the hand-ons, like I'll get you through the short exercises, but like start thinking about this. How do you think that you would like to apply a robotic fabrication process by the end of this week? And just to give you some insights, I'm sharing some end effectors that we have used with the robot. And the effector means actuator, the tool that we really attached on the robot arm to do things. Because the robot is a generic machine. It's just a thing that moves in the space, that just does things, that creates a kinematic. But then it's up to us to make it flexible and to customize the motion, the kinematic, right? And we do that through end effectors, which are these tools, these elements. And we will share with you some like digital twins of these end effectors. But then if you want to try to imagine a new one, your own personal process that you would like to explore. And if you have some rhinoceros skills, then feel free to start thinking about an end effector to carry out a robotic process. And what I mean with this is that at the end of the week, we would like you to think about a form, like a process, let's say starting from like the creation of a scale model, using a hot wire cutter that can produce forms, and then you can imagine them like as small or as big as you want. These could be building components, or these could be proto-architectural ideas, concept forms. And then like that's actually your idea of a possible full-scale form. Think it makes sense? So you can produce something that is simple at the end, just give us an idea of space or an idea of tectonic, an idea of materiality. It's really up to you, up to your skills. Hopefully like these inputs will, just boost your creativity. That's really our intention. And now I'm mixing a bit. These are some results from this past spring prototyping and fabrication class. So these are actually paper modules that we created using the laser cutter. But like this, the concept remains. So like when you produce a form, always try to frame it in the architectural context. And more of the context. That's not a COVID map. I know that now it's weird this year to share this kind of maps, but that's the frequency of robots, the density of robots in the US. And again, Detroit is important. Detroit is crucial because there are so many robots there coming from the heavy industry that is a driving force of the local economy, coming from the automotive industry. And you might know the rise and fall and rise back of the city of Detroit in the past decades, tied to this specific sector. And there's a great culture of production. There's a great culture of manufacturing in Detroit. which I would consider local heritage. Literally, like the concept of manufacturing is heritage, and that's an image that comes from Ballard International. It's a company that buys used robots from the automotive industry and resells them, and that's how they get spread in schools, in specifically Michigan, but hopefully this is a best practice that is having impact in other regions as well. And I associate this to this concept of democratization of tools, and I associate this with the Diego Rivera mural at the Detroit Institute of Arts. Just a beautiful way to depict human labor that, like in the context of the fourth industrial revolution, we imagine in a different way. So in here you see like people in an assembly line, like creating this fluid form of production, while now we are imagining same processes but augmented by robots, augmented and by technology. So that's the framework. So we are like all joining from around the world, and that's awesome. But like our activities converging in one region that has a super interesting and compelling history. Yeah, just some technical details. We'll share everything. The framework of this workshop is called Inclusive Futures. We really want to share knowledge, to get in touch with people from all over the world, and to find opportunities, like for collaborations or communication. And so we will share everything online through the Digital Futures channel. Everything will be recorded, and not only the YouTube recordings, but you'll be able to access also the Zoom recordings that I'll share at the end of each session. And I'll be happy to promote your work as well. We have an Instagram page tied to the university, and if you this is a sneak peek of like some of the recent work from this past semester. And usually we just we post stuff like Bianco the robot does stuff with students, and usually we like really to document that and to share it. So this is the platform where possibly like you'll see your creative stuff promoted on our end, for sure. And so back to this notion of fourth industrial revolution, we call it infrastructure. You might know that some developments happened over time since the industrial revolution to the mass production to the third industrial revolution that included internet, basically, jumping to the fourth industrial revolution that implies the fact that tools of production are smarter, are connected, and can just, and not only in one sector anymore, not only in the sector of manufacturing, but this infrastructure is just like getting wider. And since it's, let's say, like 10 years, more or less, it got really a major topic in technological schools, regarding industrial design, but also architecture. And if we want really to look at the fourth industrial revolution at a way wider scale, including all the possible sectors revolving around it, we could call it digital transformation. And digital transformation really means it's not only like getting things in the digital form, but adding value to it, or like having that produce value, even economic value. But in general, imagine that as a social and technical change. So it changes technologies, of course, but also the culture on how we use technology. Um, and and of course, like it's very important to mention the fourth industrial revolution because architecture is a conservative sector, not necessarily an early adopter of change, of innovations. And we tend to absorb change from manufacturing, from the entertainment industry. If we think about visualization and renderings from the aeronautic industry, if we think of the work of Gary and how he managed, he understood the workflows, the design workflows to produce boats and planes, and transferred some of that stuff in architecture. So basically, it's thanks to him that we draw with the computer in our sector. And so, of course, I'm kind of like, that's a very, very like long story short, but the automotive industry played a role very important in the framework of the advancement of robotics. And what we're seeing here is Unimate, which was the first industrial robot deployed in an assembly line. And that seems obvious, but of course the robots were deployed because, like, to reduce costs of production, to protect the workers, to keep them away from difficult and dangerous tasks. But the thing is, and that's the reason why I mentioned the smart robots that are the tools of the fourth industrial revolution, like Unimate. I wouldn't consider it like from the mechanical point of view a smart robot, because how it worked basically included the repetition of a sequence of tasks. So basically, we using a sort of a joystick, basically, we programmed Unimate to reach a target point A, B, and C. And the robot did that and repeated that task over and over. And that was it. So there was no other dynamic input. There's no feedback loop kind of condition. That was just it. And just to out. So it basically was turning digital, the assembly line, or well, mechanical, the assembly line, but still not having create like an added value out of that. And to create added value, you need to add internet, you need to add connection, you need to change the stream of input and output data, and that's what's happening right now, which is exciting. And that's why these finally might have really like impactful consequences in architecture and design. I'd like to ask you another question. I'm seeing that you guys do not have expertise with Kuka, so I can just go to the second. Actually, I can also share the results. And I'll ask you a second question meanwhile, just to know if you've ever, got in touch with the topic of robotics. I'd be curious also to know, we'll have more time to discuss this, why you're interested in robotics, right? Or like or even if you are studying the topic on your own or any of these things, really, I would love to have this conversation with you guys. Oh, I'm seeing very interesting results. Who said? Can I ask to some of you who said that the term robot comes from Japanese?
I say robot come from Japanese. I think I remember when I kids I watch anime and watch some robots in that movie, and I remember that.
That's interesting. That's interesting. It's not the right answer, but that's a good point, though, what you mentioned. So nobody thinks, oh, one person thinks that robot comes from English. So the question is, the term robot comes from English, Latin, Japanese, or Czech? So the response is, and then I can see also the origin of the word robot, and the actual word, original word is robota, means programmable machine, autonomous device, or forced labor. So let's start from this, that the term robot comes from sci-fi. So it doesn't come from engineering, doesn't come from design, any of these sectors. It's basically a sci-fi play written by Karel Capek and in 1921, who was from Czech Republic. And actually in the sci-fi play, he kind of like somehow in parts of it could be described as a sort of like a political, social manifesto in which he was, criticizing the forced labor in assembly lines, or like the dehumanized work in the mass production. So means that the word robot comes from Czech and means forced labor. And also was used in a way that meant like boredom, like something that you're not willing to do, something that is just not pleasant, and is not meant for humans. And so again, the root, the original word is robota, very similar to Latin. I would say very similar to English as well, but has a different history. It comes from the 1920s. And yeah, and basically the thing is implied repetitive tasks in assembly lines, which exactly what Unimate, the first robot, did, just repeat tasks in an assembly line. So and one interesting thing, I don't know if you guys are watching the Digital Futures lectures these days, but there's a lot of conversation around AI and machine learning. And what's interesting to me is that like the first robot, like the real first robot used for real in automation wasn't a humanoid. And Neil Leach the other day was mentioning the fact that when we imagine AI, or when we like Google search AI, we see a person and a humanoid robot next to that person working in conjunction. And he's like, that's not, any of these things are real. AI means code, scripts, algorithms, and that's it. So it's interesting. And as I mentioned before, is like, like technology creates a certain culture, make us think, like make us create our own idea of a robot, of automation, or even AI. But the thing is that humans are ambitious. Humans automate whatever they can, especially those tasks that for us are boring or dull or humble or any of these things. So especially, of course, in first world economies. So like if you have the economic force to do certain things, you deploy the tools in a way that you will avoid to do things that you don't want to do. And so humans automate whatever they can, and a tough job, right, is related to the sector of architecture. And it's interesting to see how in the 20s there was a lot of innovation happening in agriculture with the objective to automate the process in the same way assembly lines were automated. And if we think about agriculture, and if we think about the US as an application case, beginning of last century, 90% of people, more or less, worked in agriculture, while today the number is close to 10%. So just to see really how these things can change completely. And there are currently many European projects funded by the European Union to develop robotics in this very sector of agriculture for like one specific reason that not necessarily is to automate certain things. Now there's a lot of machinery in the sector, but like to save water. So basically now the systems that we use in agriculture, actually I will rephrase this in this way, 70% of global freshwater usage comes from agriculture. And now we have intelligence, we have global intelligence, we have machines, we have algorithms, we have data to control these things very, very precisely. So like you put these things together, you put the algorithm, you put automation, and you really can advance the sectors with benefits at the global scale, considering also the ecological issues related to that. So I asked you where like the term robot comes from, and I included Japan because Japan is always been tremendously advanced. And in the 80s, automation in construction was already a thing. Robots were deployed, multitask, single task robots. And the intelligence behind this process is the fact that automation wasn't used only to do things in a repetitive way, but there was an idea of customization behind that. So it's like the use of robots was like imagined in a way that the architectural the process of making architecture could really be customized and tied on a like case by case design requests and scenarios. But the thing is, there wasn't an infrastructure already ready to accept that change. I mentioned many times the fact that if you're a bit techie or a bit nerd as I am, you might track some trends that show how like following the Moore law, like the technology evolves exponentially, very, very fast. But at the same time, looking at the market law, organizations change much slower. It's just hard for organizations to accept change. And that's the thing, like if there's not an infrastructure, it's hard just to say, okay, let's use robots, because architects are not trained to imagine the downstream processes, to design in a way that is fabrication aware, and the cost of software, it's hard. Like software is not accessible. It's hard to create platforms in which all professionals involved in the creation of architecture can communicate and share data. So there are like many, many things. Actually, these are all the reasons why we don't build with robots right now. It was just like a great intuition in the 80s. Something in Europe happened as well, but for sure the avant-garde was in Japan, but there was no culture, there was no infrastructure, things were expensive, the tools were expensive, the robots were expensive, software were expensive. So like now, this conversation is back now in the scientific community, because sort of a perfect storm is being created. And due to the current fourth industrial revolution, the current accessibility and democratization of technology. And so now there's more room to try again and to push innovation in construction. And yeah, but just to go back to the notion of architects, designers, and master builder, we don't make things, right? We make drawings of things. And if you are familiar with Mario Carpo, great professor, great books, he talks about architectural representation as an art of notation. And in the Middle Ages, designers were like Brunelleschi, they were able to understand construction, to understand the tools of construction. And then we got to the Renaissance, in which intellectuals were thinking and advocating for the importance of ideas over craft. So ideas were more important. The intellectual work was a major thing, and so from that point, design and making started to diverge. And now we're trying to get that relationship back, just like to put back together design and making through smart processes downstream. And as I mentioned, certain tools are coming from manufacturing, from the automotive industry, etc. But now that designers are having this kind of discussions, now new tools are being, crafted and adjusted for architects. So like the robot is just a machine that has arms, but now like these are examples that come from ETH Zurich. Architects are realizing that if we want to deploy this kind of tools in construction, we need to hack them. We need to have, for instance, robots sitting on movable platforms. We need interfaces. We need to be able to design with Grasshopper, for instance. We need to use the tools that we know in our design process, and we need to transfer that design phase into robot implementation or digital fabrication in general. So like these changes are happening. Many research centers are now adapting robots to architecture. And one major thing, in addition to the fact that robots can move in the building site, is the fact that they can see the world around them. They can understand, like geometric constraints around them. They can understand if people are walking around the building site. So like there's all these emerging technologies that are really the consequence of this adaptation in architecture of the tools that come from other sectors, from other industries. And just one example, I'll share more soon, but just one precedent that like puts together all the things that I'm trying to talk about that shows the potential of large-scale fabrication. And so this is the DFAB house, designed and produced by ETH Zurich, great researchers, Gramatian Color Research and Block Group. That created this prototype of housing prototype that like for the fabrication, basically all techniques are included, like additive fabrication, subtractive fabrication, smart construction, combined construction, all these things together. So one robot, sort of like a 3D printing material, one robot creating the reinforcements for the concrete wall, and just trimming 2x4 wooden objects to create the structural shell frame for this prototype to work. And back to this notion of we need the infrastructure, we need the platforms, we need to understand certain things. Basically, this is what we're gonna do. We'll use Grasshopper with called Kuka PRC. It's for beginners, and so meaning that we have a certain level of flexibility, but it's just a great way to start. It's intuitive, and you'll see that in a second we'll be able to generate an animation, a digital twin of our robot that exists in real space, and we'll have it in our computer, and we can, simulate things. We can understand the script, we can fix mistakes or fix collisions before testing anything in reality. And so you that testifies really how the culture of design is changing and how now we can access this design thinking strategy as well. I'll get more specific just to talk about the fact that, you know, when we design in Grasshopper, in Kuka PRC, we are designing a process. Like, you are designing the way the robot moves in space. And then, of course, you have to imagine what the outcome will be. You have to imagine, you know, the final object you want to create or to cut or to 3D print, whatever you want. But the thing is, you're actually designing the way the axis, you know, occupy the space. And you are connecting time and space, because time matters as well. The speed matters as well. And when you, especially when you test the material and you see the hot wire cutting foam, and you wanna figure out what's the best way to do that with which input and output parameters. And so kinematic, you're designing a process, and that process will produce a final outcome, and that's just a way, a different way of thinking, and we can do that using a generative approach. And so you'll be able to really draw a line that we call toolpath, which is basically where you want the robot to go, what path you want the robot to follow. And you will divide that toolpath into target points. So basically the robot understands only the points. And then you will change the density of points that the robot will reach. And it will go from point 0, like from start to end. And you'll be able to design all these things. To conclude, we are perfectly on time, so we have an hour to work on software stuff. This is an exhibition of the work produced a couple of years ago. Unfortunately, this year we couldn't do it because of COVID limitations. We could not go on campus for a long time. But this is the sort of physical exhibition that we had at the end of one of the Robo classes at Lawrence Tech, and I'm imagining to see this reproduced in a digital way, so that you will display your work as a sort of online celebration, online exhibition of your efforts. So that's for the introduction. Of course, drop comments if you want to ask questions, or just to communicate. I'll share this lecture as well as Google Slide or PDF here. And so let's jump into the module 1, let's call it. So we have instructions for the assignment. We have submission template. And then you guys, if you didn't do that already, please download these 2 files. And if Kuka PRC worked, you shouldn't have issues downloading it. In the email that I sent you, does it work on Cartesian plane? Yes and no. It depends on what you mean. We'll see that in a second. So basically, oh, go ahead.
Yeah, so it was my question. Like when you say it is moving from point to point, but when robot is changing the angle, the plane matters. So what plane system is it working on? That was my question.
Yeah, it's a good question. And no, it works in the 3D space. So basically, in the 3D space, and every point has an X, Y, Z, and A, B, and C. So each point has, with Cartesian space, I mean like the flat plane, which is not how the robot works. Just like for each point, it records information about 3 rotations and X, Y, and Z. So where the point is in space. And the zero, and I'll show that in a second, the software, the zero is the base of the robot. So that's the origin. And then you have a positive direction for everything. Positive X or negative, positive, negative Y and Z, and positive rotation, either like counterclock or clockwise. We'll see that in a second. If you have other doubts, we can discuss more. Yes.
Great. Thank you, Sarah.
Yeah, absolutely. That's exciting. So again, I'm just yeah, go ahead.
I wanted to tell you one more thing. Like, I requested the access for accessing these files from Google account. So if you can approve it, that would be great.
Oh, sure.
Thank you.
Let me do that. Can I do that? Oh, well. Sorry, maybe I shouldn't stream this. Yeah, I shouldn't stream this because maybe there's your private stuff. Let me come back here.
Thank you, Sarah.
No problems. No problems. But I need to find it though. Well, I'll do it in a second. So meanwhile, I'm sharing this. So there's no need to go through the submission slides format. Okay. I'm accepting that now. I'll go through. Yeah, let's go through this. Just useful for me. I'm opening this and I'm accepting all the requests. Give me a second, guys. Okay, let me know if you guys can accept. There is give me a second, guys. More requests in the inbox. Okay, let's see. Did other people join meanwhile? How many? There are 15. One person joined. Who joined later that I didn't interact with?
I did. Hi.
Hi, nice to meet you. How are you?
Great, thanks. I'm Espartaco from Argentina.
Oh, great. Thanks. So one question for you. Did you receive everything, the folders?
Yes, everything.
Were you able to install Kuka PRC?
Yes.
Awesome. Great. So, okay, I see you here. And anyway, you guys feel free to reach out whenever you have questions. Now I have the inbox here open as well. Okay, let's see. Another person might join soon. So, okay. So the easiest thing, and then Emily, let me know if you want to talk about that later when we see. Actually, yeah, if you want, if you feel comfortable when we get to the slide with your demo, you can go through that if you want. So today's exercise is called, well, it's basically the robot going through a maze, and the toolpath is a polyline. It's very simple, but is an exercise that has basically all the main components that we need to learn to understand robotic programming with Grasshopper PRC. That's just for you to see the real setting. We have the build lab. There's our Bianco, the robot, on a white stage. We built this maze, and and you'll see when you open the Rhino file, you'll see the digital model of the maze as well. And what I'm asking you to do is to go through just, to draw. We'll do it together to draw a polyline, and we'll see how the robot will navigate the target points. One thing is, like, if you guys are comfortable or able to use OBS Studio, and you want sort of immediate feedback from me, you can use it so that you are streaming the Rhino file as your background. And so, like, if you're calling me, it's just easy for me to pin your videos and to guide you and to help you. So that's the process. We'll see if that works. We'll see. There's one video for a couple of years ago. We'll see also what it means to jog the robot manually with the joystick. And Emily recorded a couple of great videos that explain the differences between joint mode, axis mode, or world coordinate system mode. And so basically, when you model, and we are seeing 3 levels here: the axis mode, the world mode, and the auto mode. The thing is, when we jog the robot with the joystick, with the teach pendant, that's the right name of the object, of the tool, we can control either every single axis, or we can follow the world coordinate system given by a predefined by the machine X, Y, and Z in the positive or negative directions. There's just another, and that's important because when you try it in the physical space and you jog the robot, you really understand where the negative is, where the positive is, what it means, the rotation of each axis, and you really have a sense of what's going on and how to control those things. Because in Grasshopper, the more we advance with scripts, we are able to control the orientation of the planes. And so by understanding how the planes rotate in space, you're also adding to that knowledge the understanding of the robot's behavior. So that's why this exercise is relevant to understand the logic. More videos. That's something that you will export today. We don't necessarily need to run your scripts because it just will be the same for everyone, and this will be what you guys will produce. It's just really the robot going from start to finish. And as you can see, the students had some agency in finding also creative ways just to document this process. But if I advance, okay, so in here, we'll start. So that's a video that shows how to, hopefully I'm not wrong, that's the world coordinate system. And I don't know, Emily, do you want to explain what you did, or you want me to do that? It's up to you.
Yeah, sure, I can explain it. First of all, I'm really terrible at jogging it in axis mode. It's a lot harder than doing it in world mode because you have to think about every single axis of the robot and know which axis to move and in which direction to move it. So basically, you've got those buttons on the right-hand side of the robot, and you have to hold down a trigger to activate the robot there. And then basically those plus and minuses on the side there is what controls the robot. in access mode, you can see right here, this is like really difficult. The controls are a little bit backwards from what you would think. So, and they actually say on the robot where the positive direction is for each axis and where the negative direction is. But it's a little hard to keep track of when you're actually jogging it. So sorry about that. I'm like really terrible at it. But so basically I'm like moving the second and the third axis of the robot, and then you use the large axis, which is like the base, to move it from like left to right. And then the other ones are on the arm a little bit further. But for world mode, it's a lot easier because on like the teaching pendant, you'll just see X, Y, and Z. And then it's like really logical at that point. So you can just move in the X direction versus the Y direction. And then if you need to move it up for some reason, move in the Z. So that one's a lot more logical and it's easier to use because the whole robot kind of functions together and you don't have to think about each individual axis.
Yeah, and you guys might understand now why, from the previous video, why we attached a spring on the robot arm because we wanted, to make sure that collisions are not an issue. And so, like, students, while doing this exercise, even if they hit the floor, it doesn't really matter because the end effector was flexible enough basically to absorb the force that came from you punching the maze. But yeah, thanks a lot for this demo. You will find these videos. I dropped all the video demos in one folder, in the shared folder. It's really like an easy way for you to understand what it means, really to understand the behavior of the robot in space. And the zero is there. The zero is down there. More images, students being creative and while carrying out this exercise. But like, let's get to the point. That's the script. That's it. I believe that I uploaded for you only the second part, which is the Kuka PRC part. I'm asking you to add just a couple of components from Grasshopper. And that's the thing. You design everything in Grasshopper or Rhino. I mean, it's fine if you use the hybrid workflow. Then at the end, no matter what you have designed, no matter the form, based on the production process that you have in mind, the robotic process that you have in mind, you break the geometry that you want to realize into target points. So that's the procedure always with Kuka PRC. And all that part is Grasshopper part. Once you have the points, the target points, from that point on, you have the Kuka PRC part, which ends with a component called core, Kuka PRC core. And we'll see different kinematic modes. But basically the inputs are the simulation slider, the kinematic mode, the tool, the end effector, which in this case is the long spring, and the robot, like the real robot that we have, that we can pull from the library and reproduce the one that we have in the lab or whatever big or small robots you want to use for the process. So here's the assignment for this day. So I'm asking you to produce one image, one or more images. This could be the expectation, but really try to use this in a way that could fit nicely your portfolio. So represent the robot, show the robot. There are many ways to do that. You can take screenshots, you can render very easily the geometry. You could extract the wireframe of the mesh. This will be produced as a mesh in Rhino. You can take only the outline. It's really up to you. We will start working on this together. I'm giving you few hours. Just don't take more than that. Just get this done. And I really would like to discuss this tomorrow as like a starting, like is a way to kick off the meeting with you guys. Use the Google Slides template. So drop there the image or the diagrams or like your material, and again I'll be able well, at the end we'll collect all your outcomes and they will be part as an exhibit within the Digital Futures online, sharing of material, but we'll promote it through our university channels as well. These are some submissions from students, simple and simplified screenshots of what's going on, animations, GIFs, just from representation. Some students tried also to record videos like from really like different points of view inside the maze and to document that as well. Another approach, you see a bit of wireframe. This could be it's up to you if you want to keep or know the stage where the robot is, or you want to just locate it in the space, like just a neutral space. More representations, and that's our guy in the physical space. So that's the request. Do you think it's clear? Send me a reaction, thumbs up, something. Give me, yeah? Okay, awesome. Good. Great. And I'll stop this, and as I mentioned, there's all the demo videos embedded in the slides are here. And so just take a look whenever you want to deepen some of these things. Or even ask me to come back and I can just go through some of the material again. I'm asking Emily again. Emily, did I say everything? Did I forget anything? Are we good?
I think you got most of it.
Okay, good. Yeah, sorry. I'm using you just to keep track of the stream of consciousness that I'm sharing. If you think that I covered everything properly, okay, that's good. Let's go into software. And I have the completed file. Maybe it's easier if I use this, right? Yeah, let's use this. Where is it? Okay. So you guys should be in this situation right now. Is view only? Oh, sorry. Yeah, I'll change that. Sorry. I'll change to edit mode later. No problems. Yeah, that's a good point. You guys let me know if you have. So yeah, but don't send me the request individually. I'll change the status of the sharing later. It's no problem. So you should see this. Let me know if you have issues, but you should be able to see the components that I was talking about. One thing that I suggested you to install is a plugin called Bifocals, which you can call by typing Bifocals. And to me, especially when I teach, is useful because I can read the name of the components, and so that I can have here the icons, so that people that are more like visual persons can keep track of the components, to memorize the components that I'm using. So let's start. I'm starting from the assumption that you guys know how to draw polyline in Rhino. I'm sure that that's the case. So drop a line here. Oh, my layers are not locked. And actually, I can show you some stuff as well. Maybe the wood shop. These are the real proportions of the space there that for us are useful to understand, where we can sit and to collaborate with the robot to carry out tasks. I can lock the stage. This stage, actually, you can see some target points that were recorded in space using the robot. And in here, actually, it's in, it's how we did this. It was like really using the teach pendant to guide the robot toward a point in space. And we recorded the coordinates and we imported those coordinates in Rhino. Very like a simple entry-level way to just find some like just the correspondence of points in the physical and in the digital. Just because we have never done the point cloud, we have never done the survey of the space, but the precision is close enough. Oh, I'm seeing Jeff. Hi, Jeff. Welcome. Good morning. Coffee, a kid by coffee. Awesome. Great. So Jeff will help us as well, as I mentioned, guys, before with the fabrication production processes. So what we have here, produce the actual maze that we have in the physical space. So by the way, let's start from the beginning. That's Kuka PRC. You should see the label up here. You have few functions in the ribbon. We have the Kuka PRC core, which is the most important component that usually takes all our inputs. We have a bunch of modes, and we'll understand the differences actually tomorrow, especially to understand the difference between linear and point-to-point. We have a bunch of robots, like some models that are just some presets produced by Kuka. Because Kuka PRC, that's intuitive, but works with Kuka robots only. There are other plugins for ABBs. There are other ways, many other ways to program robots. Just Kuka PRC, it's a pretty, it's a fairly, known software. There are communities online, forums where you can find tutorials and information about Kuka PRC. That's why we're using it, just to facilitate your knowledge, learning experience. We have some tools and the factors. Usually we model our own tool. So the end effector is custom. And then we have some advanced components to tweak the kinematic and some other utilities. We'll use some of those. But basically, once you have learned this, you're really good to go in terms of understanding the process. So I'll explain other things in a second, but just let's see the robot. So I can clear the values. So you can call a component a curve component, and then you drop it here. Right click, set one curve. You pick it, and then you have it. At that point, what we want to do is to divide the curve, because we want to break the geometry into target points, right? So we plug the curve into my divide curve component. We can decide how many points we want. In this case, the maze is pretty simple. We just want the corner points. So like the easiest way to do that is just to add one division. And like if I unplug the toggle, it's gonna be just like the visualization of start and finish points. But then if I plug a Boolean toggle and you set it to true, then I have all the kinks at the corner points automatically. It's just a way to do that, not necessarily, not the one and only way to do that. Let's keep it simple. And then if I plug a panel, you'll see the points. You see the points. We have 17. You might know that Grasshopper starts always the list with 0, so this is gonna be 0, etc. And if I wanna plug also, let's say, a point list, and I wanna visualize those points. One thing, millimeters is the unit, simply because robots work in millimeters. So that's the reason why you have it that way. So in this way, you can see the order of the kinematic, and you can change it. You can shift the numbers. You can reverse the order. There are all many things that you can do in Grasshopper, but now the base. No, the curve is not provided in the file. Draw it. Let me know if you have difficulties with that. And to draw, you can just go to the top view, draw the curve, and then maybe you might need to bring it up once you have it. Let me know, of course, if you have issues with that. So we know that that's the 0, that's 17, so that's our last point. I think you have to draw it, guys. Now we want just to use normal. That's a recurrent sequence in Kuka PRC. Plain normal. We want an origin, and as you can see, right, and you can. If I stay there, you can read the description. You can create this plane perpendicular to a vector. And if we zoom in a little bit, can I try to do this? You might be able to visualize the planes. And we can do all sorts of operations with these planes. We can rotate them, we can orient them however we want. But now, for this exercise, we just want the robot to reach those target points, get from start to end, and that would be it. So now we have target points, and that's the order from 0 to 17. Now what we want to do is to plug, and if you use, not working usually, usually Control-Alt and click should bring you there, but so the linear movement is here. You plug your plane into this input, and you have automatically the robot appearing from the Kuka PRC core. You can, like, of course, you need the robot component to see it. Okay. And we'll explore some of things, but basically, just one preview works if you plug a slider from 0.000 to 1.000, and it goes from 0.0 to all the target points that we have set. Okay. When we get here, and maybe I can get it close enough, you'll notice basically that the axis of the robot will need to match the 3 axes of the plane. And that's simply, that's how it works. Takes a while. Just try to imagine the geometry, try to imagine the rotations. But that's the easiest way to put together all this information, and we'll get things more complicated the more we advance. Let's start from, there are a few things to be explored. For instance, let's talk about this. Linear movement and point-to-point. Let me read. Should the curve be projected onto the maze floor? Yeah, slightly above. Imagine that happening in the real space. You don't want the effector to touch the floor, just to stay slightly above and to go through the toolpath. So that's how we want to do this. Right? It's like, yeah, I don't know why I'm not locking the layers. Is it everything locked? Okay, now you can see it. It's there. Put it wherever you want. I mean, it could be higher as well, but just to use the constraints of the maze, right? Two things to know, and we'll repeat this. Point-to-point means that the robot will connect the target points in the fastest way possible. So you don't have 100% the control over the kinematic because the robot will just figure that out. And now it's easy because we have a polyline with kinks. You can do a spline as well. You can draw a more curvy toolpath in the maze. It's up to you, totally up to you. But in this case, it's easy to imagine, a line connecting the target points. And that's the point of the linear movement. Linear movement connects with a line the points, which is obvious in a polyline like this, but not obvious when we have like different geometry squiggles in the space. So fastest way possible, line between target points. Fastest way means that sometimes the robot might do rotations that simply you didn't program just because the configuration of all the 6 axes together make it easier to reach point B from point A in that specific way. So hopefully it's clear. We have other things to consider, for instance, and I always let me find something here. Sorry, where is it? Set tool. I always forget to change the values here because those are not necessary. Okay. That should be. Why is this negative 150? Can that be 0? Maybe yes, I think so. Second, guys. Yeah, that's the standard. That's the standard orientation. Okay, let's do this. So in here, we plug the custom tool, our end effector. We use this component, and then we can plug a geometry or a mesh. To make it appear here, and I can disconnect this, right? We have to drop a geometry in the origin in Rhino. Let's make disappear the stage. Let's make for a second disappear the robot, the wheel of the mouse, preview off. So you can see that the maze modeled in Rhino here and the factor, it's our mesh, is here placed on the origin. Once it's there, and you can see that if I click this, it turns green. Because if I do set one or multiple meshes, depends on how many objects you have, and you select this, and you have these objects that you can plug in the custom tool component. And at the end, when we plug it, you see in the tool, you see it appear here. The reason why I changed some values here is because we recorded these and the factor in an analog way. I'm not going through that, doesn't really matter. What you need to know is that you can set the tool number. It means that when you plug the script in the robot cabin, you have to set which tool you're using, and those things need to be recorded both in the teach pendant and in Kuka PRC. So in this case, the maze in the build lab, right, Emily and Jeff, has always been number 1, the spring, right? The spring and the factor is number 1. What we need to do is to set the length in millimeters. So as you can see, the robot has, for the end effector, its own reference system, X, Y, and Z. These are the positive directions. So you can imagine also like the settings in the negative directions. And records also rotations. It means that the tool in Z along Z, you see the positive Z, is more or less, we can simplify it. Let's do 220 millimeters. It means 22 centimeters. That's more or less, but it's fair enough because we don't have to touch the maze. So it's the level, it's enough as a level of accuracy. This is a pretty standard move to drop like a negative 90 rotation here and look at the B, which is here. You're kind of like, you see the B, this rotation goes like this. If I'm just the robot arm, the robot head, just the preset is 0 usually. And that's what we got, right? So if I run again my script, I see that that's not exactly what we want to achieve. And so this is the moment I keep opening that in my other screen where to put the rotation in the negative direction of tool B. And so we adjust that. 90, nice and clean and simple. Simple. I don't know, I keep saying simple, but if it's not, you guys let me know. Okay, so we have it. Okay, now we can explore some tools here. If you click on the Kuka PRC settings, you have here, you can just, right away, you can just export the script. You browse wherever you want to save it, is the desktop, fine. You hit apply, and you'll see a file appearing, a TXT file appearing on your desktop. I just open it. It's up here. It's good to understand it. When you open it, basically what you see the sequence of our points with the linear movement, which is recorded usually when you export it. You export it as X, Y, and Z, while you will see the rotation values in the point-to-point movement, in the point-to-point kinematic. And what you can look at is the fact that we have a start position. This is just the basic standard. We didn't change it. The tool is number 1. The speed is by default. These are the axes of our robot. We call them A. So A, 1, 2, 3, 4, 5, and 6. And then the end. So these are the things that you might look at. We'll come back to this. And that's just what you plug in the robot, basically. And the robot will just run that toolpath as you designed it. What else we have? We have some advanced settings. There are a few things that you can tweak in terms of visualization. One interesting aspect is the fact that, for instance, you can decide the start and the end position by changing these values. Let's do one thing quick, for instance. You can decide, as you can see, the robot has a standard home position. So the robot starts here, goes to the first target point, carries out the geometry, comes back home to the home position. That's standard, but you can change it. For instance, you can say, yeah, thanks, Jeff. Yeah, keep doing this. What you could do is to say, I want the robot kinematic to stop at the last program position. This might be useful, for instance, when you're designing the light bright exercise. Just you want the robot not to ruin your composition, your geometry. So you hit that, you hit apply, and you see that the second line disappeared. Because in this case, and we can run the automatic script. Sorry, I come back and I play it. I can change the simulation speed. Okay, then it gets to the last program position, and it stops there. Then automatically the visualization is up, like you didn't see the robot coming back, right? And even if we want to adjust the movements, we can do. So now to be real quick, the robot has different limitations, but we can do a range from negative 360 and 360. Let's put it to 0. Right. Sorry, this was up here. Sorry, the mouse is a bit, it's being tricky now. Here we go. I can create a, you know what, I'll plug it here for a second. Okay. Right. So now you understand like where the positive and negative rotation is. Of course, when we reach certain limitations of any axis, the Kuka PRC core will turn red. You can do this, you can do this, you can rotate it however you want. And so I can say, okay, once I'm good and I'm okay with a start position that I prefer, and you have some, you know, like the last axis is actually the little guy that rotates up there. You can say, okay, Kuka PRC settings, I want get current position as start. Apply, and as you can see, you modified the start position. Yeah, I shouldn't have done that, but anyway. So if I plug it again here, now you have this movement, so you have a bit of control over the position at the beginning and at the end, right? So this time we don't start from home, but we start from a defined location of the robot that we have decided, and the robot will do this, etc. And they will stop. As you can see now, like 100% is the last programmed position. Other things I could show you, that's just visualization. You could decide to visualize or not the toolpath. Okay, Jeff is keep giving you the tips here in the chat log. That's up to you if you want to see the toolpath shown. Usually we interpolate movements so that the robot creates target points in between those that you programmed in Rhino software. And usually when there's something that doesn't, let's plug it here again. Right, so let's see. We don't see it here, it should though. Well, usually when you, and I can change it actually with I can change it here. Let's say that I move away the maze. You see, like you basically you see how the visualization of the kinematic of the motion of the axis changes. So let's push it away. It's pretty intuitive, right? Like if the toolpath is too far, just the robot won't calculate the rotations or any of these things, right? So there are some unreachable points happening here. Like the robot cannot get there. And usually there are like, when these things happen, it's simply the robot cannot calculate the way to reach that point. And in this case, as a consequence, you see that the Kuka PRC core turns red. And so if you want to check where the problem is, you open it, you go into the analysis tab, you can zoom in, zoom out, but basically You can click on the graph and then you can check where the problem is. And if you notice that the robot is like the extension seems like forced, you might want to work on those target points just to fix the mistake, right? And like if you want to really exaggerate this, okay, there's like nothing makes sense anymore. All the points are just not reachable. It's not even able to calculate it. So let's see if I can. I mean, that's the logic, and you will see these red areas like spread in the graph, and you will need to operate that and change certain things. So let's come back to the safe zone. Maze is back. The toolpath is where we want it to be. Things are not red here, which is okay. Let's path linear. I locked it. I should lock the end effector as well. It is down there. So again, like the 0, the origin is Rhino. Rhino is the origin for the robot. And for, as Emily was showing later, is the origin of the X, Y, and Z of the world coordinate system. So when she was jogging the robot using the teach pendant, and when she was using it into like world mode, the world is this stage. That's the world coordinate system. This is the orientation as the 0 is there. So all the numbers refer to the value of the 0, that's the origin, which is the robot, the base of the robot. So okay, everything is locked. What you can do, if you wanna visualize how it works, you bake it. And you bake it, and you have a mesh. And you can decide if you wanna bake the toolpath or no, that's up to you. If you want this to be a dashed line or whatever you want. And from now you can export that, you can work in other software, or you can visualize it. Another way that allows you to control the geometry, you can plug it here, right? You can even change the color. You can mute the Kuka PRC core. Now the robot is just a mesh plugged into a Grasshopper component. And you want to change the preview. Change it. And let's mute this. You can really change the robot or do, right? Or even combine the two things once you have both the visualization and the lines here that you baked. Hopefully you guys are familiar with the notion of bake. Bake means transferring geometries from Grasshopper to Rhino, and you do that by doing, let's say, either right click on a component, you hit the egg, and then the geometry appears in Rhino. So these are a few ways to change, the visualization. You can record the screen, of course. You've seen that if you hit play and you hit the loop, the script will run until you interrupt it, so we'll keep going forever. And if you want to record your screen for documentation, that's the way to do that. I apply, and also you can visualize in Rhino, like the rendering mode, and you can change really the material, whatever you want, and like all the renderings that you have seen earlier. Can I visualize that? You can change the color of the maze as well, and then you have the visualization of a nice and clean robot. You can change the background. So it's really up to your creativity now to represent this through an animation, a GIF, a video, a drawing. You can Photoshop, you can place it wherever you want, not necessarily in the empty space. Think also about what you think is missing in your portfolio and what you would like to add. So use this as an opportunity for that. and I apply, exit, and let's see what we have here. It's, I don't know. It's a bit articulated. You could change also, the color of the mesh. You have to spend some time, selecting the item and to say like, okay, I want to color that item in, I don't know, something else, right? And then you have that as well. So when you have both on, you have the visualization of both the red, like the preset default preview in Rhino. You can mute it and just see only the, was that just already black? Okay, you can change it, right? Let's put the, orange, Kuka orange, right? You have some agency over the selection of the components, and you can add. But again, there are many items, mesh elements in this. So I believe that if we do like from 0 to, I don't know, let's say, work. Or you can even do a range and plug it, and you should be able to see what you want to visualize. And you can plug different things as well. So let's say that you want to plug, I don't know, this and this. Very random, guys, but like just for you to see how you can control these things. And for instance, we picked element 32 and 99, and you can find that here. We have a tree. If we flat it, that might change with the organization, and you have to change the different different numbers here, but just like in the 32 should be the 32nd element here, somewhere here in the tree. So we can look again these things, or if you are not familiar too much with data trees, that in this case, this tree is divided into 3 branches. You can just flatten, right click, and you flatten, and you have only one container. And so in this case, it's easier to see element 115 should be embedded though. Should be embedded in one of these. So just try to follow the, like the slider to find and to remember which element you want to select here. But it's really just a trick to represent, visualize these things. And we can even go back to the robot might be in no, that's because it's white at the moment. Turn it as it was originally. This guy at the moment is orange. We can switch it back to black. There's a white component somewhere, but that's fine. So really, I don't know. What do you want me to say? Have fun. Hopefully that's a good, this shouldn't be scary if you've never used Kuka PRC, if you've never programmed a robot. Hopefully this exercise is enough straightforward. Of course, let us know if you have any questions. I'll share in a second with you guys the slides. I'll give you the possibility to be editors. And yeah, so you have everything under control. You have other examples, references. You have, the images that I shared with you in the slides. So submit at the moment. So today you are not producing anything. So the script is the same script for everyone. look at the videos. So if you export, the TXT file that I showed you earlier, and you plug that into the robot. And by the way, the robot is from the 90s. So we are using a floppy disk drive to do that. I don't know if you guys even know what that is, but that's the technology that we are using. So if you transfer that script into a floppy disk and you plug the floppy disk in the robot cabinet, you will see the robot going through the maze, and that will be it. So we'll make things more complicated. I really would like to see some images before next session and be happy to discuss some of these tomorrow, and keep thinking about, start thinking about a possible final project. I'll find out the references for you for the connections between architectural unit or like small scale robot process, and how to imagine that at a larger scale. So that's it for today. Hopefully this exercise will require, like, I don't know, 10 minutes. It depends on how long you want to work on that. It should be simple and fast and fun. You guys have questions? Was it clear enough? Yeah? Okay. Feel free to reach out if you have more questions in mind. We'll have time to discuss. So guys, have a wonderful day, afternoon, evening. I'll see you tomorrow, and you know where to find me, and have a wonderful day. I'll see you guys. Bye everyone. Ciao. Ciao. Ciao.